Hello, welcome to the course SJ to B02 Mechanics 2. The contents of this course is taken from an introduction to mechanics by Kleppner and Kolenko. We will continue to discuss topics from module 2, central force motion. In the last class we discussed about hyperbolic and elliptic orbits. In today's session, let's talk about orbit of a satellite. So as you know, orbit of a satellite in most cases correspond to an ellipse, and depending on the value of the eccentricity, the shape of the ellipse is going to vary. Let's do a numeric problem which will make the concept clearer to us. A satellite of mass 2000 kg is in an elliptic orbit about the Earth. At perigee, which is the closest approach to the Earth, it has an altitude of 1100 kilometers, and at apogee, which is the farthest distance from the Earth, its altitude is 4100 kilometers. What are the satellite's energy and angular momentum? Also, how fast is it traveling at perigee and apogee? So this is the geometry. You have a circular or spherical Earth, and around that in an elliptical orbit the satellite is revolving around it, and these are the values given for apogee and perigee. First thing, if you want to reduce it to a single body problem, you need to calculate the reduced mass, which is given as mu equal to me into m divided by me plus m, where me is the mass of Earth and small m is the mass of satellite. As you can see from the problem, mass of the satellite is very small compared to that of Earth. If you remember, the mass of Earth is around 6 into 10 to the power 24 kilogram. Okay, so me is much higher than m. So in the denominator, instead of me plus m, you can approximate it to me. So the expression for reduced mass now gets simplified as mu equal to me into m divided by me. Me cancel, so you have m. So reduced mass is almost same as mass of the satellite. First, let's calculate the total energy. We know that total energy is related to the major axis of the ellipse. So let's calculate the major axis A. So from the figure you can see major axis is going to be the perigee plus apogee plus the diameter of Earth, which is twice the radius RE, and radius of Earth is 6400 kilometer. So A is going to be 1100 kilometer plus 4100 kilometer plus 2 into 6400 kilometers, which is 1.8 into 10 to the power 7 meters. And A and energy E are related through the equation A equal to C divided by minus E, or E equal to minus C by A. Let's now talk only about the magnitude, C by A. And C is a constant, G into small m capital ME, and we can rewrite in terms of acceleration due to gravity small g, because small g is capital G me divided by RE square. So in terms of small g, I can write C as mg RE square. So substitute for the parameters, you get the value C equal to 8 into 10 to the power 7 joule per meter. Now all the parameters are available. You can calculate energy E as minus C by A. So when you substitute for these parameters, you get the value minus 4.5 into 10 to the power 10 joule. So this is the energy of the satellite when it is in the orbit. And what is the initial energy of the satellite before launch? Before launch, the satellite is on the surface of Earth. It's not moving, so there is no kinetic energy. So the entire energy is the gravitational potential energy, which is given by minus G m me by RE, which is nothing but minus C by RE. Substitute for this, you get the value minus 12.5 into 10 to the power 10 joule. So this is the initial energy, and E is the final energy. So the energy needed to put the satellite into the orbit is final energy minus the initial energy. So this is minus 4.5 into 10 to the power 10 joule minus 12.5 into 10 to the power 10 joules, which is 8 into 10 to the power 10 joules. So this is the energy required to take the satellite from the surface of Earth and place it in the elliptic orbit. So once we are done with energy calculations, let's now turn our attention into angular momentum. And as we know, angular momentum can be calculated using eccentricity. So from the previous class, we know R minimum equal to R naught divided by 1 plus E, and R max equal to R naught divided by 1 minus E, where R naught is the radius of the circular orbit and E is the eccentricity. So from the first equation I can write R naught equal to R minimum into 1 plus E. From the second equation I can write R naught equal to R maximum into 1 minus E. I have two expressions for R naught, so I can equate them, and I do that I get 1 plus E into R minimum equal to 1 minus E into R maximum. From this, by rearranging the term, I get E equal to R max minus R minimum divided by R maximum plus R minimum. And what's R maximum? R maximum is the distance from this point to the farthest point, and R minimum is the distance from this point to the closest point. Okay. So R max plus R minimum is nothing but the major axis A. So E equal to R max minus R minimum divided by A. And what's the value for R max? This is the perigee plus radius of Earth, which is 10.5 into 10 to the power 6 meters, and this is apogee plus the radius of Earth, and R minimum is perigee plus radius of Earth, which is 7.5 into 10 to the power 6 meters. So substitute for the parameters in this equation, you get eccentricity equal to 1 by 6. And we know that angular momentum L and eccentricity E are related through this equation. E equal to square root of 1 plus 2 EL square by mu c square. From this I can write E square equal to 1 plus 2 EL square by mc square. And the parameter of interest L equal to square root of E square minus 1 mc square divided by 2E. So all the values are known. Substitute in this equation, you get L equal to 1.2 into 10 to the power 14 kilogram meter square per second. Now we need to calculate the velocities. For that we can use the energy equation, E equal to half mv square minus c by r, where the first part is the kinetic energy and second part is the potential energy associated with the inverse square force. So let's calculate the velocity at the closest point, perigee, call it as Vp, and the distance, call it as Rp. So we know the value of Rp. This is perigee plus the radius of Earth. So 1100 plus 6400, which is 7500 kilometers. So at this point, what is the velocity? So in this expression, we know what is the value of m. This is 2000 kilogram, and value of r is nothing but Rp, and value of c is known, and we know the total energy. Total energy remains a constant by virtue of the central force motion. So all the parameters are known. So when you substitute in this, you get the value of V as 7900 meter per second. Same way you can calculate the velocity at apogee, and here the value of the distance is, you call it as Ra, and Ra is going to be 4100 plus 6400, which is 10,500 kilometers. Once again substitute in this equation, you will get the value of Va as velocity at apogee as 5600 meter per second. There is an alternate approach, because we know that this is a central force motion and angular momentum by default is conserved here. So the angular momentum at this point is same as angular momentum at this point, and if you look at the orbit at these 2 points, velocity is tangential. meaning velocity is perpendicular to the radius. So angular momentum is m into r cross v. Since r and v are perpendicular, the cross product is replaced by a normal product, so you have m into r into v. So since we are talking about a one body problem, instead of m you have the reduced mass mu, right? So mu into r into v. At this point, this is mu vp rp. This is same as mu into r into v at this point, which is mu into va into ra. So mu vp rp equal to mu va ra. From this, va equal to vp rp divided by ra. Once again you get the same value, 5600 meter per second. So this is how you calculate all the parameters related to the orbital motion of a satellite. Finally, a small note. Suppose that a body is projected from the surface of Earth with an initial velocity v0, then we know that this is the energy equation, and if v0 is less than the escape velocity, then we know that it cannot cross the gravitational field of Earth. And if you put this value into this equation, you will find that the C by R term, the potential energy term, is higher than the kinetic energy term. In other words, the total energy is going to be negative. So when velocity is less than, when initial velocity is less than the escape velocity, total energy is negative. If total energy is negative, what will be the shape of the orbit? It's an elliptical orbit, right? So if you look at the trajectory of an object projected from the surface of Earth with velocity less than the escape velocity, you will find that it corresponds to an ellipse with one focus at the center of Earth. So as the figure suggests, you can see that the body invariably returns back to Earth. So you can try this. You can throw a stone vertically upwards. So you can, if you monitor the trajectory of the stone, you will find that it corresponds to an ellipse. Why? Because in this case total energy is negative and eccentricity is less than 1, and that corresponds to an elliptical orbit. Come to the last portion, which is Kepler's law. So once again, let's revisit Kepler's law. A little bit of history. Johannes Kepler was actually an assistant of another famous astronomer, a Danish astronomer known as Tycho Brahe. Brahe was an experimentalist and Kepler was a theoretical physicist. So Brahe made a number of experimental observations regarding planetary motion, and he was able to get experimental data with high accuracy. And what Kepler did was, he did a lot of mathematical calculations and finally came up with 3 empirical laws with which he was able to fit Brahe's experimental data. So this was not an easy task. It took him almost 18 years to come up with these empirical laws, and these laws are famously known as Kepler's laws. Kepler's first law says that each planet moves in an ellipse with the sun at one focus. So this is something we have discussed in the last section. So this is consequence of motion in an inverse square law force, right? Because in that case you have a potential energy having the general expression minus C by R, and if you write down the energy equation, you will find that the total energy is negative, and consequently the orbit corresponds to an ellipse. Second one we have discussed in this chapter, also in the last semester's course. Radius vector from the sun to a planet sweeps out equal areas in equal times. This happens because gravitational force is a central force, and by default angular momentum is conserved in a central force field motion. So the Kepler's second law is a consequence of conservation of angular momentum. Kepler's third law, which is also known as the law of periods, says that the period of revolution T of a planet about the sun is related to the major axis of the ellipse A by the relation t square equal to ka cube, where k is a constant which is same for all planets. So let's try to prove Kepler's third law. So let's start with the definition of angular momentum. So we know that L equal to mu into r cross v, and if you are taking the polar coordinates, then velocity v has two components. One is the radial component and vr, and second one is the tangential component v theta. R and vr are parallel, so when you take the cross product, that's going to be 0. And r and v theta are perpendicular, so when you take the cross product, that's going to be a normal product. So the magnitude of angular momentum is small l equal to mu r v theta. V theta is nothing but r into d theta by dt, so L equal to mu r square into d theta by dt. Now, if you multiply on either side with dt by 2 mu, then you get L dt by 2 mu equal to half r square d theta. Now, what is the term on the right hand side? Half r square d theta. Now, if you look at the geometry, suppose you have an elliptic orbit. This is the center, so r is the radial vector. Suppose you have an angular displacement of d theta, then this side is going to be r d theta. Now, if d theta is very small, then the area of this section can be approximated by the area of this triangle. And what's the area of this triangle? Half into base into height. Base is r, height is r d theta. So the area of the triangle is going to be half r square d theta. So this is the differential element of area. Now, in one complete period, the whole area of the ellipse is going to be swept up. Now, how do you calculate the whole area? So remember, this is an equation with respect to time. So if you integrate it with respect to time, so you have, suppose capital T is the time required for one complete cycle. So on the left hand side, you have L by 2 mu into capital T. So in one complete cycle, the entire area of the ellipse is going to be swept out. So on the right hand side, you have the total area of the ellipse. If A is the semi-major axis and B is the semi-minor axis, then the area of the ellipse is given by pi into A into B. So L by 2 mu into capital T equal to pi AB. Now semi-major axis is nothing but half of the major axis. So small a equal to capital A by 2. We know the expression for capital A. This is C by minus E. So small a is equal to C divided by minus 2E. And the semi-minor axis B is given by L divided by square root of minus 2 mu E. So this is from the last section of this chapter, which I am going to give as a reading assignment, properties of an ellipse. So for now, you just take this result. You will find the detailed derivation in your reading assignment. So once you get to the values of A and B, I can make some manipulations in this equation. From this equation, I can write T equal to 2 mu pi AB divided by L, or T square equal to 4 mu square by L square, pi square A square B square. Substitute for A and B. You get T square equal to pi square mu C square divided by minus 2EQ. But we know that A equal to minus C by E. So instead of minus E cube, I can write C cube by A cube. So when you substitute for A cube, you get T square equal to pi square mu divided by 2C into A cube. So you can see on one side you have T square, other side you have A cube. So let's convert these parameters into a more familiar shape. We know that C equal to G into M, where capital M is the mass of Sun and small m is the mass of the given planet. And the reduced mass mu is given by capital M small m divided by capital M plus small m. So when you make these two substitution in this equation, you get T square equal to pi square divided by 2 into capital M plus small m into G into AQ. And what does Kepler's third law say? It says that T square is proportional to A cube, right? T square by A cube is a constant. So if T square is proportional to A cube, then this term has to be a constant. Let's check out that. Pi is a constant, capital M mass of Sun is a constant, gravitational constant, it's anyway constant, but look at this term, small m. This is not a constant, right? It varies depending on the planet. But look at the denominator, you have capital M plus small m. If you look at the solar system, majority of the mass is concentrated at the Sun. In other words, mass of the Sun is much higher than mass of any planet. Even if you take the heaviest planet, Jupiter, its mass is 1,000 times less than the mass of Sun. So capital M plus m can be approximated to capital M. So all these are constant, so T square is proportional to AQ. So you can say Kepler's law holds pretty good in the case of the planetary system. And this is true for any satellite system. For example, if you take Earth and any planet around Earth, either it is Moon or any other artificial planet, you can see that in all these cases, Kepler's third law holds good. So here a number of artificial planets are given. So all these have different values of eccentricity and major axis and the time period. So in this case, the orbit corresponds almost to a circle, but in this case, it's an elongated ellipse. So you have completely different trajectories here, completely different values of time period. But when you look at the ratio of A cube to T square, you find that this is a constant. So that's why we say Kepler's third law is valid even in the case of satellite system or in the case of the solar system. So this is a pretty good achievement because Kepler gave this law in the 17th century, and that time all the sophisticated telescopes were not there, and the mathematical tools or the mathematical resources were limited. Still, he was able to make such telling contribution to the field of astrophysics, which is valid even today. So before winding up, as I said, there is a reading assignment for you. This is the last portion of the chapter, the properties of fields. So with that, we come to the end of module 2 on central force motion. In the next class, we will start a fresh discussion on module 3, harmonic oscillators. Thank you.